Hello, this is Martin from the University of Michigan. I am happy to share recent work in grounded open vocabulary acquisition through fast mapping in vision language models. I would like to thank my collaborators, Jia Pan and Joyce Chai. As humans, our acquisition and use of language is tightly bound to our sensory motor experiences in the physical world. A human reader will easily ground noun phrases to the corresponding entities in the image. This ability to connect language units to their reference in the world is referred to as grounding, and it plays an important role in the learning and understanding of word meanings. Even when the term is generators new to human learners, they can still locate the target objects in the perceived world and acquire its meanings. In fact, such ability to bootstrap new word learning with only minimal information, known as fast mapping, is universal in human language acquisition. Recently, there has been a substantial effort on pre-trained vision language models. Despite their exciting performance, it remains unclear whether these models can truly understand or produce language with their grounded meanings in the perceived world, and how grounding may further bootstrap new word learning in a few shots. These questions are interesting scientifically and also from the engineering perspective. Even with the availability of grounded vision language datasets, namely the image-text pairs with fine-grained word-object mappings, the costly grounding annotation can hardly cover the whole vocabulary space during the pre-training. Building upon pre-trained models, it is important for the agents to have the ability to learn grounded new words in a few shots of broad text image pairs without explicit word-object mappings. Therefore, we introduced the grounded open vocabulary acquisition problem. Under the GOVA formulation, the model first pre-trains on a grounded dataset with fine-grained annotations of word-object mappings for a set of base words. Further, the model needs to acquire unseen words from the few shots of broad text image pairs. There has been a lot of evaluations for grounded language acquisition, but unfortunately, they fail to serve our purpose. A lot of the tasks focus on language condition object detection or visually grounded language modeling. However, they either leave the language modeling unattended or ignore the referential uncertainty. For example, the model could have mistakenly cited the larger white boat in the image as the evidence, while the true reference of the word is actually the smaller yellow one. Given this limitation, we evaluate a vision language system through both language modeling and object localization tasks to get the best of both worlds. On language modeling side, we use the log pseudo-perplexity to evaluate the language modeling, which is the negative log probability of producing the correct word from the context. On the object localization side, we use the intersection over unit as the metric. We also introduced the multi-model metric, log-grounded perplexity. It combines the two unit-model metrics and can be interpreted as the negative log probability of producing the correct tokens and pixels. Therefore, the grounded perplexity serves as a comprehensive evaluation. We now introduce w2w, our computational model for this study. As a dual-stream vision language model, image and texts are encoded using pre-trained language models and ResNet backbone. Vision language representations are fused using self-attention in the cross encoder. For a typical VLM, language modeling is performed on this fused representation. We, instead, are motivated by recent advances in detection transformers. The object decoder takes a set of learnable object queries and produces the object representations. Masked language modeling is then performed upon the object representations, and this makes our ungrounded baseline. The complete model with grounded pre-training is additionally tasked to produce word region alignment, which is to match the produced objects to the corresponding text spans in the sentences. Now let's look at some findings from the grounded pre-training. Does grounded pre-training really help the model to learn faster? Yes. We found that the model outperforms its grounded variance in all the metrics across time. After 100K steps of pre-training, the model is able to compete with strong pre-trained baselines, which either suffers from poor language modeling performance or poor localization. Also, we noticed that the model has a surprising performance in localizing unseen words behind the masks. Here we show some examples of the model's performance in unseen words. This performance disparity in language modeling and localization suggests that the model has developed some ability of doing word agnostic grounding to localize the most likely referent of a word through the linguistic and visual context, even if the word itself is never seen during pre-training. This ability opens up the opportunity to enable human-like fast mapping when learning new words in vision language models. Now we proceed to the few-shot new word learning. Under this setting, there's no explicit bounding box annotations, so we freeze the detection grounding objectives and only fine-tune the model with language modeling. We find that the model demonstrates strong fast mapping ability of unseen words without significantly forget the seen ones. with a fast acquisition of the unseen words from as few as 8 occurrences. We finally seek to identify the predictors that can explain or anticipate the performance of the model. We selected a set of linguistic, perception, and psycholinguistic metrics as the predictors and performed likelihood ratio tests. We found that the vision language models still heavily rely on the distributional statistics, similar to the unimodal language models, and that the model does better in localizing and acquiring concepts which are visually salient and less ambiguous, consistent with human learners. We also find that the model aligns well with human intuition for imageability, but not for concreteness. This highlights the model's capability of learning words from visual perception, but fail to acquire the tangible but generic concepts, which requires physical interactions. We finally note a misalignment between human perceived familiarity of the words and the machine's perplexities. Namely, the more familiar humans are with a word, the more perplexed the model gets. This still warns us of the cognitive implausibility of these large vision systems. More research is needed to understand the cognitive underpinnings of human language acquisition from the computational perspective. For more information and details, we kindly refer to our paper. Thank you.